This video will cover simultaneous equations and the use of instrumental variables to estimate models with endogenous independent variables. By the end of this video, you should feel comfortable explaining the meaning of endogenous and exogenous variables, solving a system of simultaneous equations in terms of the exogenous variables, also known as the reduced form, determining whether an equation is identified, and assessing the validity of proposed instrumental variables. Let's turn back to the hypothetical market for fresh oranges that we considered earlier. Here, quantity demanded depended on price P, while the quantity supplied depended on both price and weather W. Let's introduce two new definitions to help us talk about the variables in this model. An endogenous variable is determined by a system of equations. Notice that Q appears in both the demand and supply relationship, as does P. Both quantity and price are jointly determined by the system of equations, so they are endogenous. This is consistent with the Greek root endo, which means inside. An exogenous variable is determined outside of the system. Notice that W appears only in the supply equation. Weather affects quantity supplied, but is not part of the demand relationship. Accordingly, weather is an exogenous variable. This is consistent with the Greek root exo, which means outside. How do we estimate the parameters, the betas and alphas, of the demand and supply relationships? We might try, in stata, using OLS to regress Q on P in an attempt to estimate the parameter beta 2 in the demand equation. It is worth noting that the independent variable P is also an endogenous variable. We will see shortly that this is a problem. Recall that this OLS regression would produce unbiased estimates only if a number of conditions hold. An important one here is that the independent variable and error term are uncorrelated. Does this condition hold in this case? Think back to the reduced form equations that we derived for P and Q. We can see that P depends directly on U, a clear violation of the assumption that the independent variable is uncorrelated with the error term. Even without this reduced form, we might have reasoned that this error term is essentially a shift in the demand curve would affect both the equilibrium quantity and price. In any case, this Gauss-Markov violation means that the OLS estimates are likely to be biased. We should expect to find the same problem if we attempt to estimate the supply relationship. We could regress Q on both P and W in an attempt to estimate alpha 2 and alpha 3. We would need to consider an analogous condition that P and V are uncorrelated. The reduced form shows that P depends directly on V, once again violating the same Gauss-Markov assumption. We should find something similar in other situations. OLS is biased if one or more of the independent variables is endogenous. What are the options at our disposal to avoid this? One solution is to avoid estimating models where endogenous variables are used as independent variables. However, this is an unsatisfying approach, as there are many interesting and important models where some independent variables happen to be endogenous. For a better solution, let's revisit the reduced form equations once again. Consider estimating the reduced form equations, that is, regress Q on the exogenous variable W, and also regress P on W. What coefficients do we get on W in these regressions? A careful look at the reduced form for Q shows that W is multiplied by a number of terms, so that the W coefficient in this reduced form regression is an estimate of negative beta 2 times alpha 3 divided by alpha 2 minus beta 2. Similarly, the reduced form for P shows that the second reduced form regression has a W coefficient that estimates negative alpha 3 divided by alpha 2 minus beta 2. Looking carefully at the expressions for these coefficients, we see the only difference is beta 2. In fact, the ratio of the two coefficients is beta 2. In other words, by estimating two reduced form equations, we can compute an unbiased estimate of the coefficient on the endogenous variable P. Let's try to understand some intuition on how we did this. Clearly, the exogenous variable W is essential for us to complete this estimation. When W changes, the supply curve is shifted, forcing P to change as well. Although price is endogenous, we can think of the weather as inducing exogenous variation in price. In other words, the market for oranges does not affect the weather, but the weather does affect the market, including prices. If we consider how weather affects both price and quantity, we can in turn learn about how price affects the quantity demanded. The same condition holds elsewhere. We say that a model is identified, that is, we can estimate its parameters, if there is at least one exogenous source of variation for each endogenous variable. Let's apply this same idea to check whether we can estimate the supply relationship. The supply relationship includes an endogenous variable P. This means that we would need an exogenous source of variation in P that comes from the demand relationship. However, there is no such exogenous variable in the demand function, so the supply relationship is not identified. That means that no matter how we rearrange the coefficient estimates in the reduced form equations, we will never be able to estimate alpha 2 on its own. Let's consider a graphical illustration to confirm the rule that a model is identified only if each endogenous variable has at least one source of exogenous variation. This graph shows the supply and demand function following the autonomous convention of having the independent variable price on the vertical axis. Remember that a market data set will not tell us the supply and demand functions, only the market equilibrium at the intersection. However, we might see multiple market equilibria as one function or the other changes. In our model, weather affected supply but not demand, so as weather changes, the supply curve will shift, either outward for good weather or inward for bad weather. As the supply curve shifts with weather, we will see new market equilibria. Note that all of these equilibria lie along the demand curve, which is unaffected by weather. Looking at the equations, changes in the exogenous variable weather causes movements in the market equilibrium because weather shifts supply. Because weather does not appear in the demand equation, weather is an exogenous source of variation in the endogenous variable price. As we wait for weather to change the price, we can see how price affects quantity. These are movements along the demand curve. Note that we cannot estimate the coefficient alpha 2 on the supply function's endogenous variable. Weather shifts the supply curve itself, so we can't tell if a change in quantity supplied is due to weather-induced change in price, or if it is due to the changing weather itself. In other words, we do not have an exogenous source of variation in prices for the supply equation. Graphically, this means that the market equilibria are not moving along the supply curve as we would need to identify the relationship. Now let's dig a bit deeper into the mathematics of estimating the coefficient on an endogenous variable. We will see shortly that instrumental variables provides a great shortcut to the algebra of solving systems of simultaneous equations. Think through the steps we took to estimate beta 2, the price coefficient in the demand relationship. We estimated two reduced form models, regressing Q on W and then P on W. Recalling the mechanical calculation of the OLS coefficient, we note that the two reduced form coefficients on W are simply mathematical expressions involving these covariances and variances. Next, we divided the first reduced form coefficient by the second. With a little bit of algebraic manipulation, we see that the two variants of W terms cancel out, leaving this ratio of covariances. A careful comparison of this expression to the formula for estimating an instrumental variable's coefficient reveals that they are one and the same. We are dividing the covariance of the dependent variable in the instrument by the covariance of the endogenous variable in the instrument. This leads us to the following shortcut. To estimate the coefficient on an endogenous variable, we can use an exogenous variable, in this case weather, as an instrument for the endogenous variable, in this case price. With this shortcut under our belts, we can easily complete the estimation in Stata using the IV regress command. As we have seen before, we must specify both the endogenous independent variable P and its associated instrument W in parentheses in that order with an equal sign in between. Before we get ahead of ourselves, let's make sure that the instrumental variable we identified meets the three criteria. First, the instrumental variable must be correlated with the endogenous independent variable. We saw earlier that the instrument W causes a shift in supply, leading in turn to a shift in the market equilibrium, including a shift in price P. This would suggest a correlation between the two. We could also see this relationship more directly from the reduced form for price. Here we see that the endogenous variable P depends directly on the proposed instrument W. The second criterion is that the instrumental variable is uncorrelated with the error term. Here, the instrumental variable W enters the supply equation, but the error term of interest is in the demand equation, that is, the model we're trying to estimate. If we believe the system of simultaneous equations is a good approximation to reality, that is, weather really does affect supply but not demand, then the second criterion is satisfied. The third criterion is that the instrumental variable is not already in the model. We can see easily that the proposed instrument W is not in the demand function we are trying to estimate. We may want to think of the second and third criteria together. In essence, they say that the instrument W is not a part of the demand model, nor should it be. In other words, we must be convinced that demand for oranges is independent of the weather. If that's not true, then weather is correlated with the demand model's error term U, violating the second condition, or we would need to add weather explicitly to the demand model, violating the third condition. If we wanted to offer a critical view on the validity of this instrument, we might argue, for example, that consumers like to eat oranges more when the weather is warm. This direct effect of the proposed instrument on the demand would invalidate either the second or third criterion. As before, we must rely on this kind of reasoning rather than performing a statistical test when discussing the second and third criteria. As an exercise, let's turn back to the airline market, where we believe that weather affected demand but not supply. Try answering the following questions. Which variables are endogenous? Which are exogenous? Which equation or equations can we identify? And how would you estimate beta 2 and or alpha 2? When answering these questions, feel free to use the instrumental variable shortcut discussed in this video, although of course it is also possible to answer these questions by solving the system of simultaneous equations. You may wish to pause the video here to work through the exercise. Let's discuss the answers, starting with the first question. Inspecting the system of equations, we see that both Q and P appear in both equations. As with the model for the market for fresh oranges, price and quantity are endogenously determined by the market. By contrast, W appears as an independent variable only in the demand equation, making it exogenous. The second question is which equation or equations can we identify? In the demand equation, there is one endogenous independent variable, so we need an exogenous source of variation in P. We should look for this in the supply equation, but unfortunately there are none. Supply contains only endogenous variables. Accordingly, the demand equation is not identified because there is not an exogenous source of variation for the endogenous variable price. Next, let's look at the supply equation. Supply also has an endogenous independent variable P, so we turn to the demand equation to look for an exogenous source of variation. Now there is such an exogenous variable W. The exogeneity of W in the demand equation enables us to estimate the supply equation, so supply is identified. Finally, let's turn to the last question. How would you estimate beta 2 and or alpha 2? Beta 2 is a parameter in the demand equation, but we just determined that demand is not identified. By definition, this means that we cannot estimate beta 2 or the other parameters in the demand equation. The reasoning is the same. We do not have an exogenous source of variation for the endogenous variable. We also just determined that supply is identified, so we should be able to estimate alpha 2. Recall our logic. Supply has an endogenous independent variable P, but the demand function offers an exogenous source of variation W. Accordingly, we can use the instrumental variable strategy, where the exogenous variable W is an instrument for the endogenous variable P.